Welcome to Dr. Jed's continuing series on calculus. Today's section is section 4.2 from Rogowski, if you missed last Friday's lecture right before spring break, or you just want to catch up on it. So what we're going to cover is extreme values. Remember, I called this the most critical section of the book. That's because it covers what's called critical points. There's a pun in there, but it really is important. First, we're going to talk about what a local or a global extreme value is, extreme being max or min. We're going to talk about where they exist, then we'll mention this critical value part, this critical point, and then how you use them to find an absolute min or an absolute max on a closed interval, and then do some examples. So first, what are they? What is an extreme value? Here's a graph. Extreme values are minimums and maximums. So for example, the graph goes down here, comes back up, goes down, up, and so on. Right here, goes down, comes back. That's a minimum. It's not the minimum for the whole graph, so it's a local minimum, not a global one. But if you look for the whole graph, there is an absolute minimum here. You could also call it a global minimum. There are two kinds of words that are often used interchangeably. For this kind, it's either an absolute minimum or a global minimum. This kind would be a local minimum or a relative minimum. Books use them completely interchangeably. So I'll try to be consistent here, but there is no complete consistency in literature. Now notice, these are local or relative maxima. There is no absolute maximum. Why? Because the graph keeps going on up and up. Not every graph has an absolute maximum or minimum. For that matter, not every one of them has local ones either. What graphs do? How do you know? So that leads us to our next point. Where do they occur? There is a very powerful theorem called the extreme value theorem. It says if f has a derivative on a closed bounded interval. Now closed means it includes its endpoints. Bounded means it has endpoints. So you might think, why is that second condition even important? Because if you look at the entire line going on to infinity, that's considered closed because it's not missing its endpoint. But there is no endpoint at infinity, so it's not bounded. So closed and bounded, if it has its endpoints, then it has to attain its absolute minimum and absolute maximum. They must occur. In other words, if you go from here to here, you're going to have a biggest and a smallest. You have to. Now, where do they occur? It just tells you that they do. It doesn't tell you where. So in order to find out where they occur, we're going to talk about critical points. C, for a graph f of x, C is a critical point if its derivative there is 0, or if the derivative doesn't exist. Now let's go back to this graph for a second. What are the critical points? You come down here, the derivative is the slope. So where is that? Right there. Horizontal tangent line means a slope of 0. So that's a critical point right there. Again, slope of 0. Again, slope of 0. These are critical points. And notice the correspondence between them and the maximums and minimums we're going so far. Now it's not perfect. If we go right here, there's a slope of 0 right there. And that's not a max or a min. So it's not always perfect. It doesn't completely match up. Critical points are not the same as maxes and mins, but they're related. Up here. Now the slope is not 0 there, but there is no slope. The slope is undefined. That's also a critical point. And down here, the slope is undefined. So that's a critical point. What do we do with these? How are critical points related to maxes and mins? Let's take a look over here. Fermat was a mathematician from a long time ago, and he had this theorem. It's a very big theorem. He's got a lot of theorems. This one just simply says, if you have a local maximum or a local minimum, then where it occurs is a critical point. And as we saw, being a critical point does not mean you are a local max or min. But being a local min or a local max does mean you have a critical point. Now how do we use this? Well, basically we're going to find all critical points and see which ones are maxes and mins. That's what the main part of chapter 4 is about. Not just this section, but all the way on. That's why this is so, excuse the pun, critical. Because knowing where these points occur, these are the most interesting and important points on the graph. Now, for our purpose today, we're going to use them to find an absolute min and max the extreme value theorem guarantees. Well, the extreme value theorem says they're there, but it doesn't say where. So what we're going to do is find all critical points. And then if you think about it, other places that are important are the endpoints. Take a look at this graph. It goes down, up. Critical points are these three in the middle, but the max occurs at one of these endpoints. because that's as big as the graph gets and then it stops. So our list of points that we're going to check will be all the critical points and all the endpoints. We're going to make a list of all the endpoints, which is to say 2 endpoints, and all the critical points, put them together, and see what we have. How do we know where the function's biggest? Well, we try them out. Whichever has the biggest value is the max. Whichever has the smallest value is the min. If that kind of makes sense, that's good. But let's try an example and see if it really does make sense. Here's a function, a cubic. Where's the absolute min and max of this? Well, what do we do first? We need to find the critical points. So the critical points, that has to do where the derivative is 0 or where it doesn't exist. So we need the derivative in both cases. The derivative, hopefully this derivative is not challenging to you. 3x squared minus 6x minus 9. Now we need to know, where is that 0 and where does that not exist? Not existing is things like errors in functions, dividing by 0, and so forth. There are no problems whatsoever with this function. This exists everywhere. But it can be 0. So let's set it to 0. So let me write that it's either 0 or it doesn't exist, and we're not worried about that it doesn't exist, because there aren't any right now. How do I set this to 0? Well, this is a quadratic, so we could factor it. I see that, conveniently, it's got a 3 factored out of it. And then furthermore, well, you could use the quadratic formula if you can't factor this. But this one was set up so that it does factor. And the 2 factors are going to be what? 1 and minus 3? Or maybe minus 1 and 3? 1 and 3. And I want to multiply back and forth the middle terms to be minus 2. So does that work? Let's see. X squared minus 3. 1 x's and minus 3. So that makes it all work. So that means x plus 1 is 0, or x minus 3 is 0. Now technically, there are 3 things multiplied together at 0, so the third thing that could be 3 equals 0. Can 3 equal 0? The answer is no. So that's not going to give a solution. What about x plus 1 equals 0? That could, if x is minus 1, or here x equals positive 3. Now those are the critical points for this function. But our goal is to find the absolute max and min on this interval from minus 2 to 2. So we need to see, are these critical points actually there? 3 is not in there. It's not going to be our answer because it's not in the region we care about. This one is. So now what do? We need to know, is this a max or a min? Is this a max or a min? Or is this a max or min? And the way we tell is by plugging them into our function, just to see which is the max, which is the min. So f of minus 2, f of positive 2, those are the endpoints, f of minus 1. Those are our only choices. One of them is an absolute max, one is an absolute min. Plug them in the original function, not in the derivative. Because remember, the derivative, the endpoints, we don't care, and the derivative here is to be 0. That's not interesting. What's interesting is the original function. So minus 2. So minus 2 times to the third. So minus 8 minus, that makes 12, so that makes minus 20. So minus 20, but minus minus makes plus 18. So that's minus 2. Minus 2 plus 1 is minus 1. What about if we plug in positive 2? 8 minus 12 again. So that's minus 4. Minus 18. So minus 4 minus 18. Minus 22 plus 1 is minus 21. Now those are both small. What about with minus 1? Minus 1 minus 12 more. That's minus 13. Minus 13 plus 9. Minus 13 plus 9 is what? Minus 4. Plus 1 is minus 3. So we have an interesting setup here. It looks like plus 2 is the smallest. So this would be the absolute minimum. It also looks like this is what? the absolute, well wait, this is the absolute maximum. And there's something wrong with my calculations, because that does not intuitively work. So minus 8, minus 20, plus 18, minus 2, that is right, 1. Where did I go wrong? Big question. 9, minus 3. I'm going to start over.